In our storm and water damage and participate in a rescue operation courses, we introduce the principle of IYT as a simple technique to assess the angle formed when two elements of a roping system are joined together. Now, usually in those courses, this is about assessing angles in a rope at an anchor point, whether that's a single sling wrapped around a large object such as a tree or a vehicle, or multiple independent ropes coming in from a load-sharing anchor. Now, the principle tells us that an ideal anchor should look like the letter I. The angles formed by our two system components should be close to 0 degrees. A yes anchor, or an acceptable anchor, should look like the letter Y, and a terrible or T anchor looks like the letter T. I wanted to spend a little bit of time talking about three slightly more detailed aspects of anchor angles that pertain to roping systems. Firstly, what are the angles at which an ideal anchor becomes a yes anchor or a yes anchor becomes a terrible anchor? Secondly, how do we estimate these angles in the field when we're not likely to have a protractor handy to allow us to accurately measure angles? And thirdly, why should we even care about this? It's all well and good to learn a principle, but if we don't understand the rationale behind the principle, why would we put it into practice? So those are the three things I wanted to talk about. And with me today, I've got a nice fat tree branch above my head. And you can see we've got a fairly standard ideal anchor set up here. If I suspend a mass, the angle formed by these two legs of the anchor is pretty close to 0 degrees. Now, above these slings, I have two load cells. These will report the exact load being placed on each anchor point, and at my feet, I have a 40 kilogram mass. Right, so what we're going to do is, starting with our classic ideal 0 degree anchor, we'll suspend the 40 degrees from our anchor, have a look at what the load cells tell us about the amount of load on each anchor point, and progressively increase the angle at our anchor to look at what happens as we transition from an ideal to a yes and through into a terrible anchor. Okay, so as we watch our mass swaying slightly in the breeze, we're seeing anywhere between 6 and 14 kilograms on each anchor point. As the wind dies down, it is starting to settle at the 10 kilogram mark. Definitely not 20. One wonders whether these weights are half as heavy as they suggest. So there we go. Our ideal anchor looks reasonably good. Although as we move it slightly side to side, we see significant deviation in the amount of load that is shared between the two anchor points. So we've now adjusted our anchor so that the angles formed by the two anchor points is about 30 degrees. How do I know it's about 30 degrees and not 10 degrees or 50 degrees? So this is the first very handy technique for estimating anchor angles in the field. Stretching apart my index and middle fingers, the angle that's formed between these two fingers is about 30 degrees. So I can line those up with our master point, and that lines up really, really well. So I'm confident this is about 30 degrees. At 30 degrees, the maths tell us that we should be seeing, for what we now think is a 20 kilogram rather than 40 kilogram mass, 10.3 kilograms at each anchor point. Our load cells, the one on the left is flickering between 8 and 10 kilograms, and the one on the right is fairly constant at 14 kilograms. Now, one unfortunate consequence of backyard testing is that our tree is not absolutely horizontal. Because the anchor point on the right is predominantly downwards, it's going to be carrying a slightly larger proportion of the mass. And just to reiterate, so at 30 degrees, we expect each anchor point to be seeing about 53% of the mass. We've increased the angle between our anchor points now to about 90 degrees, which is about the angle formed by my thumb and forefinger. So it looks like a fairly clean 90 degrees to me. 90 degrees is typically what we consider to be the transition point between an ideal and a merely acceptable or yes anchor point. Less than 90 degrees is ideal. Once we hit 90 degrees, we're in acceptable territory. At 90 degrees, with our 20 kilogram mass, we would expect to see 14 kilograms on each anchor point. That works out to be 72% of the load. So we are still reducing the amount of load felt by each anchor point, but not by a great deal. Looking at our load cell readings, we have 14 kilograms on our left anchor point, which is bang on what we'd expect. We're currently seeing 22 kilograms at our right anchor point. So ideal, less than 90 degrees. When we're looking at our 0 degree, supposedly perfectly ideal anchor setup, we noted that any side-to-side movement in the load resulted in a significant reduction in the amount of load sharing occurring. We went from reading about 10 kilograms on each anchor point to reading anywhere from 6 to 14. It turns out the sweet spot for ideal is about 30 degrees. At that point, we've got little sideways force being induced into our anchor points while being able to support moderate movement in the direction of the load. So for me, an ideal anchor is between 30 and 90 degrees. As we've seen, an acceptable anchor starts at 90 degrees. Let's move on to the next critical angle. We've now moved our anchors such that the angle formed from our anchor points at our load is about 120 degrees. Now 120 degrees, a reasonable estimate, is stretching apart my thumb and my pinky, and you can see the angle meets in my hand. That should be about what we get here. Looks like I may in fact be slightly over 120 degrees in this setup, but it's a reasonable approximation. Now 120 degrees is a really important angle when it comes to assessing anchors. At 120 degrees, we expect each anchor point to experience 100% of the load. So with our 20 kilogram mass, we expect both anchor points to be experiencing 20 kilograms of force. Having a look at the readings on our load cells, we can see 26 kilograms on our left anchor point and 22 kilograms on our right anchor point. So the numbers back us up, thinking that this may be, in fact, a little over 120 degrees. This can be a little surprising when we first encounter it. How can, from hanging 20 kilograms from an anchor, our anchors experience a total of 40 kilograms, or in this case, 48 kilograms of force? Now at all angles, our two anchor points are going to be sharing, hopefully equally, but sharing the downward force that is being applied by our load. What happens as we increase the angle between our anchor points is that we're introducing an increasingly large sideways force in our anchor points. And you can tell this simply by looking at the anchors, right? Our anchor point on the left is being pulled significantly right, and our anchor point on the right is being pulled significantly left. Those two forces need to balance each other out because they're not moving, it's a static system, but that's where the extra load comes from. As our angle increases, we're not just pulling down on our anchor points, but also pulling sideways. And 120 degrees, as we said, it's the key point. This is where we're no longer load sharing between our anchor points. Each anchor point will be seeing 100% of the force that we put on the system. Now, this isn't necessarily a bad thing. If both of our anchor points are suitably strong, if we've got two bomb-proof anchor points and we're using multiple points to allow us to place our focal point at exactly the position that we want it, then there's absolutely no problem with going to 100 degrees and potentially slightly above 120 degrees. However, if we're using multiple anchor points because we don't have confidence that any one of them is sufficiently strong, then reaching 120 degrees is the point where your system is likely no longer to be safe because you're no longer load sharing. So if you've set up multiple anchor points because you need to share the load because you're using marginal anchor points, the angle between them needs to remain less than 120 degrees. As we said earlier, we want it to remain in the ideal spectrum of around 30 to 90 degrees, remembering that at 90 degrees we're still placing 72% of the load on each anchor point. So we may well want to ensure that our angles are less than 90 degrees. Beyond 120 degrees, the forces at our anchor points increase exponentially. Once we exceed 120 degrees, it becomes very easy to quickly exceed the safe working load of our equipment and of our systems, which could obviously have catastrophic consequences. So because I can't show you angles above 120 degrees today, let's just have a quick look at some numbers. At 150 degrees, with, again, a 20 kilogram mass, each anchor point should experience 38 kilograms of force. That's close to double the amount of force being applied to the system. At 160 degrees, Again, with a 20 kilogram mass, each anchor point will see 58 kilograms of force, getting close to 3 times the amount of force that we're applying on the system. Increasing again to 170 degrees, we would expect 115 kilograms of force to be experienced by each load from our 20 kilogram mass. So that's from 20 kilograms, we could produce 150 kilograms. If we apply a standard single person plus equipment load to 170 degrees then, that would look like close to double the safe working load of 11mm comantle rope, for example. So a quick recap. I said I wanted to talk about 3 things. Number 1, our key angles. So our key angles in an IYT context, ideal 30 degrees to less than 90 degrees. Yes, or acceptable angles, 90 degrees to 120 degrees, and terrible angles above 120 degrees. Secondly, we were going to look at some ways that we can easily estimate these angles in the field. So a quick recap there, including a few bonus angles that we didn't speak about. 30 degrees, 45 degrees, 60 degrees, 90 degrees, 120 degrees. Thirdly, why do we need to care about this IYT thing? Now, I hope having looked at a few different angles, that's pretty clear now. The reason we need to care is that as our angles get larger, the force at each of our anchor points becomes increasingly large, to the point where if we exceed 120 degrees, we can very quickly reach forces that will damage our equipment and potentially have catastrophic consequences.